In this video, I want us to work on the MNIST dataset and to train it so we can identify digits and classify them to the correct class. The thing is, in this video, that I want to focus on the problem of overfitting and how we can deal with it, how we can minimize this problem using validation data. So first, what is validation data? Validation data is some of the training data that we take aside in order to use it during the training process, but not as part of the data that we use for the training itself, but as a benchmark. And what I mean by that is that after each of the epochs, after we train our model with the training data, we're going to see how well it does when we use it on the validation data. So the training data itself is going to be used to train the model, to train the neural network, and the validation data is going to be used to see how good the network performs on data that it didn't train on. The idea here is to reduce overfitting. So what overfitting is? Overfitting is what happens when our network does too good on the training data. So instead of just learning the problem in a general way, in a way that can be later generalized, we learn the specific data, the specific problems that are given to us during the training. So instead of training on the data, we basically memorize it. So if we have any outliers or any kind of noise in the training data, we're going to learn it as well. That's not what we want. We want to learn the underlying message of the data. We want to learn the pattern. We don't want to learn the specific examples that are given in the training data. And that's why we use the validation data. So on every epoch, we're going to train on the training data. And as part of this training, we're going to see how well we do on this training data. But then we're also going to check how good we do on the validation data. Now, after enough epochs, we're going to see an interesting phenomenon where we keep improving for the training data. So the loss of the training data will keep getting down. It will keep getting smaller. But the loss for the validation data won't improve anymore. So at the beginning, both of them, the loss for the training data and the loss for the validation data, both of them will improve. But at some point, we will have discrepancy where the loss for the training data keeps improving, while the loss for the validation data doesn't improve anymore. That's when we want to stop our training, and we're going to see how we can achieve it. So let's start by importing everything that we're going to need. Now, as I said, we're going to work on the MNIST dataset. So let's import the MNIST dataset. And to do it, we're using the load data function that's built into the MNIST dataset. Now, as you can see, when we import this dataset, we're going to end up with two categories. We're going to have the training category, and then we're also going to have the testing category. And for each of these categories, of course, we're going to have the images and the labels that say which of the 10 possible digits this image describes. So if we only have training data and testing data, where is the validation data? So the answer to this is that we don't really have it out of the box. We need to split the training data into data that we're actually going to use for training and for the validation data. So first, let's decide upon a ratio. How much of the data that we have for training is actually going to be used for training, and how much of it is going to be used for validation. And I call this number a cutoff, okay? So everything below this cutoff will be used for training, and everything above this cutoff is going to be used for validation. So zero index of the shape of the training images. So this is going to be 60,000, okay? So overall, we have 60,000 images in the training category. And out of them, I want 90% to be used for training and 10% to be used for validation. So if I take the number of images that I have in the training data, which is this, okay? Index 0 of the shape of the training images, and I multiply it by 90%, I get the number of images that are going to be used for actual training. Let's now split these images, the train images, to these two categories, training and validation. So the images for training are going to be all of the images whose index is lower than the cutoff. And all of the images whose index is bigger than this cutoff are going to be used for validation. So this way we split all of the images we got from the dataset for training to both of these categories, training and validation. As for the testing images, I didn't change anything, I just copied the array we got directly from the dataset, and these images are going to be used for testing. I now normalize all of the images in the three categories by dividing the value of each of the pixels by 255. Because when we get them from the dataset, each pixel is going to be in the range of 0 to 255, and we want it to be in the range of 0 to 1. Okay, so we did that for the training images, for the validation images, and also for the testing images. So now I want us to take a look at the shape of each of these arrays. Great. So we can see that each of these images in all of the categories is an image of 28 pixels by 28 pixels. This is great. Now, how many images do we have for each of these categories? So when we got the images directly from the dataset, we had 60,000 images for training and 10,000 images for testing. And as we just saw, we split the training images to the two categories, training and validation. And as a result, we now have 54,000 images for training, 6,000 images for validation, and 10,000 images for testing. We're going to do the same thing for the labels, because of course for every image we have to know the label it represents. So that's great. These are the labels that we got directly from the dataset, and these are the labels that are going to be used for training. And as you can see, it's every label whose index is less than the cutoff. As for the images whose index is bigger than the cutoff, they are going to be used for the validation, okay? So these are the validation labels. And as for the testing labels, we're going to use the very same array that we got from the dataset itself. So let's see how many labels we have of each category, as we did with the images. So we have exactly the same numbers. We have 54,000 labels for training, 6,000 labels for validation, and 10,000 labels for testing. Next, I want to convert each of these labels from just a number to a vector of classes. In the dataset itself, each label is only represented by a single number. So for example, if the image is an image of an 8, of the figure 8, we're going to have there 8. But for the training process, we want to represent it a bit differently. We want to have an array of classes. So each of these values is like the probability that this figure is each of the classes. So all of the values in this vector are going to be 0, except for the value that represents 8. And this is going to be 1, okay? Because we have 100%, we are completely sure that this is an 8. And this is how we achieve that. We use the two-categorical function. And here, as you can see, we define the number of classes. Now I want to flatten all of the images, because right now they are represented as 2D arrays of 2 dimensions, and that's because every image has a length and a width, and I want to represent each of the images as one long vector. So to achieve that, we can use the reshape function, which simply takes the same values but rearranges them, and this way, instead of having images, 2D images, we're going to have vectors that represent the same images. So first, we got the correct dimensions. Let's take a look here at this line. So here we got the shape of the training images. And this shape is going to have 3 dimensions. First, we're going to get how many images we have for this category, for the training images. And then we're going to get the size of an image. So how many rows every image has, and how many columns each of these images have. So the number of images, and then the dimensions of the image. Now notice that here and here, I didn't define any variables, and that's because I know that they're going to be the same values I got here. Because I know that the dimensions of all of the images in all of the categories are identical, there is no point in getting the same value of 28 over and over again, so I just get it once from here, and I'll use it for all of the images in all of the 3 categories. What is going to be different though, among these 3, is the number of images. And now that we have all of these dimensions and the sizes of the images, we can flatten the images. Okay, so this is how it's going to look like. We take this array of images and we're going to reshape it. And this does not change. The number of images we had before is the same number of images that we want, but we want each of these images to be represented as a long vector. So only one dimension instead of rows and columns, only one dimension whose size is the number of rows times the number of columns. Let's now define the model itself. And we're going to have 3 layers. So we have the input layer, and we have to define the size of this layer. So this is what we got here when we flattened the images, this multiplication of rows and columns. And this is how the input layer looks like, right? Each of the pixels of the image is one of the neurons in this input layer. Next, we have a dense layer of 128 neurons. Now, as for the output layer, of course, it's going to have 10 neurons, and that's because it represents 10 different classes. The output of our network is the probability of each of the classes. What is the probability that this image represents a 0? What is the probability that this image represents a 1, and so on? And as for the activation function, for this layer, I chose softmax, which is what we usually want when we talk about a classification problem with multiple classes. Next, we need to compile our model. And now we can use the fit function to define the way we want to train our model, our network. These are the images that we're going to train on, and these are the labels of these images. So this is like ground truth. Here we define the number of epochs, and here we define the batch size, which basically determines how frequently we update the weights of our network. And here is what I want you to notice. Here we define the validation data. So this is not part of the training data. This is like the benchmark. This is something that we're going to use at the end of each epoch to see how well our network did for data that's not part of the training data. So it's going to train on these images, but our metric, the way that we decide how good our network did, is using the validation data. Let's run our program and see the training in action. And as you can see, at the end of each epoch, we see two different values. We see the loss, and this is the loss as computed against the training data. And here we can see the validation loss. So this is on the validation data. And as we said, we didn't use this data for the training itself, only to see how well the network did. Now, as you're going to see, it improves, okay? So at the beginning, both of them improve, so it's getting lower and lower, and it's correct for both the training data and the validation data. But at some point, what we're probably going to see, and we can see it here, the loss function for the training data keeps getting better, and as you can see, for all of the 10 epochs, it got better for each of them. But that's not the case for the validation data. Here, the loss function, at the beginning, it got lower and lower, but here we got the lowest value of them all. And once we kept running more epochs, it didn't improve anymore. Okay, so it fluctuates a bit, it gets worse and then better and then worse again and then better again. But the idea here is that the best value was achieved here at epoch 7. So everything beyond that is overfitting. Generally speaking, there is very little point to keep going beyond this point, and it doesn't generalize well. That's why in such cases we usually use early stopping. And by early stopping, I mean that, okay, I see that I don't improve against the validation loss anymore, I want to stop my training. And since this need comes up so often, it's built into Keras. So let's see how we can change the way we call our fit function a bit to make use of early stopping. So first we need to define our early stop. Okay, so here is early stopping, and of course we had to import it from Keras. Now here we set the monitor, and it basically says what is the parameter that is the deciding factor for the stopping. As soon as we stop getting better against this parameter, and in our case it's the loss of the validation data, we want to stop our training. And then we have another parameter which is called patience. And that's because, as we saw here, it fluctuates. So sometimes there may be cases where the loss for the validation gets worse, but only for one epoch, and if we wait a bit, maybe one more epoch, it's going to get even better than what it was before. So we don't necessarily want to stop our training as soon as we got a value that's not better than what we got in the previous epoch. We might want to wait a bit more, and this is what this parameter decides. So in this case, once we get 3 consecutive epochs in which the loss of the validation data didn't improve, we want to early stop, we want to stop our training. And here is another very important parameter, and what this parameter decides is if we want to restore the best weights we got. So at the end of each epoch, we're going to have some set of weights. Now, if this parameter is on, if we did have early stopping, we're going to restore the weights that we had. So if the loss for the validation data got worse, we're not going to use the last set of weights, but we're going to use the weights that gave us the best value for the validation loss. And of course, we have to pass the early stop to our fit function. So let's add it here. And let's try to train our model again, now that the early stopping is enabled. Okay, so as you can see, we did not complete the 10 epochs. We only ran 9 of them and then we stopped. So why is that? That's because here we got the best value for the validation loss. And then we got 3 consecutive epochs in which the validation loss was worse than what we got here. And as you probably remember, we set our patience to 3. And that's why when we got 3 such consecutive epochs, we stopped the training. As you might also remember, we also have restore best weights on. And it means that the weights that will actually be used would be the weights that we had at the end of this epoch, and not any of the weights that were calculated later. Let's now evaluate the performance of our network against the test data. Now, the idea here is because we use the validation data, we are probably going to have something similar to what we had for the validation data. If we didn't use validation data and we only had the loss value for the training loss, we wouldn't know what we can expect. But since we did use the validation data, we know that the best result we got was this one. So we can assume that the loss function that we're going to get for the test data is going to be around this number, something similar to this number. So let's run it and see. Okay, so this is how we evaluate our model against the test data. And the result of this function is the loss for this data. So in our case, the loss for the testing data. So let's run it and see what we get. So this is the best value that we got for the validation data. And here is what we got for the test data. And as we expected, these values are pretty close. Let's now run a few predictions on the test data, and let's see what our network predicts, and then compare it to the real labels of these images. Okay, so we're going to predict the labels for the 21st images from the test data. Now, as you remember, the result of the prediction is an array of 10 classes. Now, of course, we don't really care about the values that we get for each of the classes. We only want to know which of the classes got the best score. That's why I used argmax. So we're going to print these predictions, and then we're also going to print the labels of the first 20 images, and then we can compare them. So here we can see the predictions of our network, and here we can see the real labels. So it seems that the network had one mistake over here, but apart from that, for 19 out of the 20 images, it predicted the correct number, the number that the image actually represents.